Okay, so the existence of a limit, page 36 here. You guys know this, right? The left-hand side and the right-hand side have to be the same in order to have a limit exist, right? So we already said that, just saying that that from the left has to equal L, and from the right it also has to equal L, and if they're both the same, then our limit is equal to L. Okay, we got that. All right, continuity on a closed interval now, and we're not going to do too much with this in a little bit. Basically, what it's going to tell you here is it has to be continuous on the whole inside part of that interval, okay? And at these endpoints, it has to be, you have to have a limit, a one-sided limit on that endpoint. So I have to have the limit equal the function right here, right, on the left. So the one on the left, that's my A, is on the left. So from A, approaching A from the right has to equal the value of my function there, and approaching B from the left has to equal f of B. Okay, so that kind of makes sense. It's basically saying that your limit has to equal those values on those two endpoints. And then it would be continuous on that whole closed interval. Okay, so when we're going through the steps, we just kind of have to process all of those steps. So the first step, we're looking at a continuity of the square root of 1 minus x squared. So that's kind of like the graph we just did. It's that semicircle. It's just at 1, -1, and 1. Okay. So we're discussing this continuity. Okay. And so what we really have to look at is just these steps above here to see if those things are true. So the first part is to say, is it continuous on the open interval from A to B? So step 1, I would be like, yeah, f of x is continuous on -1 to 1. Okay, that's the open interval. And you can just say that by looking at the graph, right? That's good enough. Because it's continuous everywhere on that inside part. And now what I have to do is I have to look at the right-hand limit over here at -1, and I have to look at the left-hand limit over here. So let's look at the right-hand limit at -1. Well, what is the right-hand limit at -1? Yeah, it's equal to 0. Okay. And then let's look at the left-hand limit at +1, right? What's the left-hand limit at +1? It's also 0, right? And this is equal to the value of my function at -1, and this is equal to the value of my function at 1. And so since the limit is equal to the value of my function and the limit is equal to the value of my function at those two endpoints, therefore f of x is continuous on the closed interval from -1 to 1. It's basically, in order to get it continuous on a closed interval, you have to check your endpoints. It's pretty basic. But you kind of, and a lot of this, you're going to find this happens a lot in calculus. You're like, totally obvious, but yet you still have to go through the steps and just kind of prove it. And use all that sort of terminology and symbols and stuff like that. Okay. All right, last part, properties of continuity. Talks here about what you can do with continuous functions. So if b is a real number and f and g are both continuous, then this is true. So you could take, like, if you knew that f was continuous and you multiplied it by some scalar b, then that would also be continuous. You could add two functions together that are, if this one function is continuous, the other one's continuous. If you add the two together, then it's also going to be continuous, right? Or subtract them, multiply them together, or take their quotient. Okay, as long as the denominator doesn't equal 0, you're good to go. All right, so all of that stuff will carry over for continuity. Let me show you what I mean. These types of functions are continuous at every point in their domain. Makes sense. If we have a polynomial function, right, every point in their domain for that polynomial function is going to be continuous in there. A rational function for every point that doesn't make the denominator 0 will be continuous. A radical function, again, for every point in their domain, always continuous. And your trig functions, obviously for tan, cotangent, secant, and cosecant, where you've got your asymptotes, it's not going to be continuous, but those aren't part of their domain. Okay, so that's why it is continuous everywhere. All right, explain why each function is continuous at every point in its domain. Well, all that you're looking at here, you have x, which is technically a polynomial function. plus sine of x, which is a trig function. And since you have a polynomial plus a trig function, since polynomial is continuous everywhere, since a trig function is continuous everywhere, therefore this would be continuous everywhere. And again, it's always in the domain. Now in this case, the domain for both of those is all reals, so that would be continuous for everything. Same idea with this next one, right? You have a scalar. Scalar, you guys, it's just a number times a trig function. So you have a product of a scalar and a polynomial, or a trig, sorry. And so therefore, again, it'd be continuous everywhere in domain. Now this one, because it's a tan function, you are going to have asymptotes, so your pi over 2's, right? So it would be continuous everywhere except for those asymptotes. Then here, what do I have? I've got a polynomial on top. I've got a trig function on the bottom. I'm taking the quotient. And so you can do the quotient of a polynomial divided by a trig. Again, therefore, continuous everywhere. So the things that are not going to work are going to be like your piecewise, right? Your crazy weird functions, right? So if I took like a polynomial and took a radical of it or something like that, right? So, but your basic addition, multiplication, division, those are going to work. Okay, but if you're doing other weird operations, raising it to the 1/3 power, stuff like that wouldn't work. Okay. That part's pretty easy. All right, let's do our last part, testing for continuity. So this theorem 112, continuity of a composite function. If g is continuous at c and f is continuous at g of c, then the composite function, f of g, will also be continuous at c. That kind of makes sense, right? Your composite function. So if you plug in a c and it's continuous in that first function, and then that g of c is also continuous, then that would have to be continuous. All right, describe the intervals for which each function is continuous. So let's kind of think about these graphs and talk about where they're continuous. So your tangent graph. How was graphing on that quiz yesterday? That sine of 3x? Oh, sorry. Close your ears. Seriously, you guys? Period equals 2 pi over b. Units equal period divided by 4. Yeah, we all forgot it. But no excuses, you guys had a calculator.
I grabbed that.
You still had to label your axes, right? Okay. So we still need to remember how to graph trig stuff. So let's graph a tangent graph. At negative pi over 2, pi over 2, pi over 4s. Yeah, these are asymptotes, right? And then we go, this is at negative 1, 1. Okay. And then this graph does repeat itself. I think sometimes we get so stuck on just that, right, one period. It's a repeater. So it keeps going, and it keeps going, and it keeps going, right? So what is the continuity? I want to describe the interval on which it is continuous. Well, it's continuous everywhere except for what? Except for those pi over 2's, right? Can we do this with that k notation? Right? So where would it be continuous? So you would say f of x is continuous everywhere except when x equals what? Pi over 2 plus pi k. That's what I like. Plus pi k. That would work. Right? So basically you can take your first asymptote wherever it is, and then you add on the period times k. That's going to work every time, because that period will then repeat it. Right? And then you should always remember, every time you're using that k notation, you would always label it where k is an integer. All right. This one's a little different. This is the sine of 1 over x, which was, if you guys remember that one, that was the oscillating function. You guys remember this guy? that we did when we talked about oscillation. So it's telling you at 0, we're at 0. But then this oscillating guy, it kind of like comes in like this, and then it does this like bam, 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 bam thing. And it comes back out. So this was on the, I oscillated between -1 and 1 the whole time in there. But then it's also telling us that we do have this random point at 0, 0. Okay. So let's do our test for continuity. Step 1 said, is f of c defined? Well, it's defined everywhere, and we're going to just examine it at 0 because that's really our big question here. So f of 0 is equal to 0. They told us that. Step 2 asks about the limit, though. So what's happening with my limit as x is approaching 0? Because this was an oscillating function, what's happening to my limit? It's what? Since it was oscillating, what did we say when functions oscillate? Does not exist. You're exactly right. So I still have a DNE here. Even though that there is a point, right before that point I'm doing -1, -1, -1, -1, -1, -1, -1, right? So it's not converging towards 0 anywhere. Even though there's a 0 there, it's not actually coming closer and closer and closer to 0, right? And so that's why that doesn't exist. So since it doesn't exist there, it's not continuous at x equals 0. And so therefore this function is continuous. And it tells us to discuss continuity. So we would say it is continuous from -infinity to 0, and then union 0 to infinity. So I'd say everywhere else it is continuous except there. All right, this last one, I don't feel like it's that important. You actually have to use the squeeze theorem here. This is one you would graph on your calculator. This is probably the only place you're going to see me talk about the squeeze theorem again. When you graph this, I know I only have a couple more minutes left here, it gives you this graph. Now this one does get closer and closer to 0, and then it comes back out. So notice how it is kind of getting closer and closer, and then it is telling us that at 0, I am at a point of 0. So since we could use the squeeze theorem to squeeze that in between two functions and prove that there is a limit there, the value of my function is 0. The value of my limit is also 0. Because it's converging toward it because of squeeze theorem, okay? And so therefore, since those two are the same, f of 0 is equal to the limit as x approaches 0 of f of x. Those are exactly the same. Therefore, I would say continuous everywhere. Okay. You guys are going to practice. Oh, what's homework tonight? Hold up. Did you guys find it? Homework tonight, pages 39, and then on 40 to 42, you're just going to do odds, and then tomorrow night, you're going to do the evens on 40 to 42. And then a couple more. But tomorrow's really just a practice day, and we're just going to go through and practice a lot and finish, do some warm-ups and some more pages and stuff like that. All right, so homework tonight, odds only, 40 to 42. And page 39, all of it. And I would say start memorizing continuity of a point word for word. And I am done.